Okay, so we when we stopped in the end of the last class, we were discussing the role of an inverter to give you amplification, right? So the chain of thought was we would like to replace the resistor in a common source amplifier with an active device, and we replaced. And when you have to replace it with an active device, you have to make sure that the resistor is replaced by something where, looking into the same terminal, you get a drain, not a source, which means that you need you cannot have a NMOS. You need a complementary device, and which, as it turns out, is a PMOS that we are familiar with. And then we said that, if this is supposed to be behaving like a current source, if that is supposed to be behaving like a current source, I can as well mirror the current from somewhere else and feed it here. Then we argued that I can use the GM of that transistor also to increase the effective short circuit current, right? So we said that we will do this. And in order to give negative feedback, we have to connect in such a way that the negative feedback still holds. Otherwise, your inverter can go in. It has so many more points of operation. It can go either NMOS being off or linear or saturation or whatever. So you'll have to ensure that your negative feedback still holds. That is, you look at the output drain voltage and feed the necessary information back to the input, and you can apply your signal. It's RS, it's RF, or this was, we call it as R infinity, right? And you get the output here. Okay, so this is a standard. This in fact is a very popular topology nowadays, especially because your voltage supply is very low in today's technology. So you cannot really afford to lose headroom just for biasing. So you essentially use whatever you get. So now an obvious problem with this architecture is, if we don't have any current mirroring and all, if this is what it is, an obvious problem is who is setting the current through the NMOS and the PMOS. Okay, so what do you think? What is happening? Let's say this is M1, M3. Who is setting the current through this DC current, quiescent current through M1 and M3, or how is it getting set? So for the DC picture, I can basically remove your signal source and all, right? I can only consider the inverter. And is there a current that is going through R infinity? No, right? So if there is no current going through R infinity, for the purpose of DC, I can as well assume that this is a short, right? For the purpose of DC analysis. So who is setting the current through this stack? Okay, you can keep it open circuit, but if you keep it open circuit, what is the relation between, let's say, VG and VD? At DC, what do you want this? What do you expect this relationship to be? I am transforming this to this, right? So on the left-hand circuit, what do you think is the relation between the gate and the drain at DC? They're equal, right? But if you keep it open circuit, then it's not equal. So you need not remove the R infinity. You can keep the R infinity here as well. I just removed it just to show you that essentially keeping that R infinity doesn't, or shorting it will not affect your DC quiescent point operation. It will definitely affect the AC picture. But as far as DC is concerned, it doesn't affect because no current is flowing through R infinity, and you have both VG and VD to be identical, at identical voltages, right? So now who is setting the current ID? Why not M3? Both M1 and M3 are in kind of a common source configuration, right? Then who is setting? VDD can be changed, but let's assume VDD is not changing right now.
Both M1 and M3 drain is connected to gate. So
correct.
Information is coming from both the.
Correct, right? So both of them are playing a role in setting ID, right? So this is what you normally do if you have taken digital IC design courses. Then you'll see that we approach it from another perspective, that what is the inverter characteristics? Yeah, V0, yeah, VI, let's say, or let's say VD, VG, the way we have marked it. So inverter characteristics is something like this. And we try to see where VG is exactly equal to VD, because we have connected it through R infinity, which is not taking any current. VG equal to VD means a straight line of slope 45 degree. And wherever you cut it is your VD, is that quiescent point, right? Which is VM in this case. Okay. So obviously this place is somewhere both transistors are in saturation. And since these both transistors are in saturation, you can apply the saturation drain current equation and figure out, and you can neglect channel length modulation for figuring out what will be the output VD, because VD and VG are identical. Okay. So essentially what boils down, what it boils down to is the fact that since this is not a constant current source, no constant current source is setting the current, it is being set by the relative strength of M3 and M1. Correct. So if M1 increases or M3 increases in strength, these characteristics will move left or right. Okay. So, and also if threshold voltage of M1 or M3 changes, let's assume let's assume it is under some condition you have ID of 1 milliamp. Okay. And let's say threshold voltage decrease for both M1 and M3. Okay. So what do you think will happen to this ID? Let's assume, what I'm saying is that let's assume this threshold voltage was 1 volt in both cases. VTN and VTP were both 1 volt. Okay. And it changed to 0.5 volt suddenly. Then what will happen to this ID? Will it remain same? Will it increase, decrease?
ID will go faster than before, because now.
You mean ID will increase?
Yes.
Okay, do you agree ID will increase? You don't seem particularly confident. Right. But both of them threshold voltage decreased. Threshold voltage decrease means if you had the same VGS, the overdrive increased essentially for both. So if overdrive increased for both and your current have to be balanced, right? So means what? Not necessarily, right? You don't have adequate information, but you have information of what is going to happen to the current. Let's assume it's a voltage. You have a common source amplifier biased with a constant voltage. Okay, then a threshold voltage decreased in an NMOS common source amplifier. What will happen to the current? It will increase, right? So in this case, let's assume that M1 and relative strength of M1 and M3 are same. Starting off, we assume the relative strength of M1 and M3 are same, which means mu Cox W by L is same. Threshold voltage is same. So those are same. Now I'm saying nothing else has changed, but threshold voltage has decreased in both cases by same amount. Which means relative strength of M1 and M3 are still same. But since the threshold voltage has, if the relative strength of M1 and M3 are same, this VM point will not change. Right? So if VM is not changing, which means the VGS of neither M1 or M3 is changing, which means the overdrive has increased in both, which means current has to increase. Right? So which is equivalent to a constant voltage bias circuit where the threshold voltage has changed. Now the voltage is being derived, is being set by the relative strength of M1 and M3, not by a separate current source, not by a separate voltage source. Okay, so which essentially means that this, if the threshold voltage drops, if VTH drops, this ID will increase. This is like a classic voltage bias circuit. Okay, so which essentially means that your GM is not constant to ambient temperature variation. So this is a problem with the inverter based circuit. So your none of your small signal parameters are very immune to ambient condition change. Okay, so you change your threshold voltage, you change your mobility, your I will change. Since the quiescent will change, your GM, GDS and everything will change. And if you are depending on, if your overall system is depending on some range of values of GM, GDS and everything, then you might face problems. So, so the reason I'm spending some time on it is because these type of circuits are getting more commonplace. So I'll not spend too much time on this, but you should know that these type of circuits are commonplace. If you go to the industry and you are trying to, or even in academia, you are trying to build circuits with low voltage supplies. These are the type of circuits you'll be facing, and these are the type of problems you'll be grappling with. So one of the ways of stabilizing the GM, as I think he was alluding to, is VDD constant. So in this case, whatever I said is true if VDD is constant. But let's say your GM has increased and you want to bring it back to a lower value. You can reduce the VDD, right? If you reduce the VDD, then effectively your overdrive will change. For the PMOS directly, you can see the overdrive will change, which essentially means that the current, since the current through M3 and M1 have to be same, which means the current will drop. If the current drops, your GM can be brought back to the original value. And vice versa. If your I0 has decreased, you can increase VDD to bring back those. So those things are done using negative feedback. Again, and this is not a part of this course, so we'll not go into that. But you can essentially control VDD using negative feedback and to keep the current constant or even the small signal parameters constant. Okay. So any questions before we move on?
Here we assume that they are relatively equal.
Yeah, so this analysis is based on, I haven't put pen to paper because if we do that, it will take another couple of classes. But yeah, so we have the analysis. The argument that I made is based on the fact that M1 and M2 are identical, but it need not be the case. So what happens if M1 and M2 are not identical? This initial starting, this graph will probably shift this side, or this graph will probably shift this side, right? It can go either left or right, but your VM point might go left or right, but it doesn't really mean that all this argument is different. The argument remains as is.
Sir,
Yes.
This thing is changing because of change in ID.
Pardon?
This all the curve are changing, it's shifting left or right.
Right.
Because of change in ID.
No. This curve can shift left or right if the relative strength of M1 and M3 are different, right? So okay. So think of it in this way. You have the middle curve, the black curve, with W by L of M1 to be certain value, W by L of M3 to be a certain value. I take this same inverter, copy it again, and then connect them node to node. Basically, two inverters connected in parallel. So do you think this curve will change?
Parallel, no.
It will not change. But what about the total ID?
Double.
It will double, right? Putting things in parallel is equivalent to saying I have doubled the size, right? So ID can go anywhere, but this curve can still remain the same.
So relative strength means individually if you are maybe on the same IC, then will
No, mu Cox W by L. Mu Cox W by L, assuming threshold voltage is same, then mu Cox W by L is the strength essentially, right? What sets the current? Mu Cox W by L overdrive squared.
So mu is immune to temperature.
Yeah, mu is not immune to temperature. What's the point?
Yes, if temperature changes, mu1 is.
Yeah, so if temperature changes, these things will change, right? Yeah. So I am not getting the point actually you are trying to get.
What I'm thinking, if it is dependent on ID, then I can separately bias it.
What is dependent on ID?
this changing, this shifting.
No, shifting is not particularly dependent on ID, right? But I gave you an example of ID can double, but still it can remain the same. The curve can remain the same, isn't it?
So how can I think that these two?
Okay, so how do you, okay, so it boils down to how do you find out VM analytically? How do you find out VM? Equating the current. So how do you equate current? You say it's mu n Cox W by L Vm minus threshold voltage. Assume threshold voltage identical both cases. This is equal to mu P Cox VDD minus Vg minus Vt whole square, right? And W by L, right? This is W by L. Correct?
So my question is, if I fix this,
Some question? Okay.
this
Yeah.
mu and Cox W, as a designer, if I fix this to voltage,
Right.
What is the problem if I?
Okay, so you can fix this voltage, but you cannot fix the current. That's the problem.
Okay.
Right? Because your mu changes, current changes, threshold voltage changes, current changes. If current changes, all your small signal parameter changes. Right? So if your system is dependent on that, then you have a problem. If the system is not dependent on that, it's not a problem. Okay. So so the argument was, if you want to keep GM same or small signal parameter same, which means you have to keep the current same to the first order. And the one way to keep the current same, since you cannot, in this particular case, you are not able to fix the current. One way to do that is control VDD. Okay. So there is one more way to fix the current, and that is also based on the architecture that we started off with, actually. So the architecture that we started off with was, you had this, and we assumed that this is biased. Your NMOS is biased, and the PMOS is set by current mirror. Right. So, and you assume this is biased properly, and which means you have somewhere, and this is set by feedback, and this is VI. So this is what was the starting point before we approach the inverter, right? So what you can also do, and what is often done also, it's not necessary to connect these two directly. You can connect these through a resistor. Let me call it R infinity in this case, or let R infinity is being repeated multiple times. 1, M3, M5. Let's say this is R3. And then what I can do, I can couple this VI and an AC couple it through a capacitor, CC. Okay. So at the signal frequencies, if CC is large enough, then both gates of M1 and M3 are seeing signal swings, but independently you can set the current through M1 and M3. It's a constant current bias. Still, it's a constant current bias. Okay, so this is another topology that is often used, but this cannot be used at very low frequencies because you have a capacitive coupling. Okay, so at high frequencies, sometimes these type of circuits are also used. You keep constant current and still use the benefits of getting double the GM.
This thing I wanted to.
Okay. The CC? Okay, so if I don't have it, what is the incremental open loop gain? GM1 by GDS1 plus GDS3. Now, if I have it, and assume at signal frequency capacitor is shorted, what will be the open loop gain? Anybody? Yush? You're saying something? What will be the gain? Now if I add capacitor and assume the CC is shorted. Right. So you'll have signal, you have VI here, you'll have VI there. So incrementally you will have current GM1 times VI. This current will also be GM3 times VI. Your GDS hasn't changed, which means your total current will, your total gain will be GM1 plus GM3 by GDS1 plus GDS3. Right? So essentially you again get double the gain, kind of for free. I mean, if you assume that capacitor is not significantly large. Okay, so that's why at moderately high frequencies, this configuration is still used. Okay, any questions? Any other questions? Okay, fine. So let's move on. I mean, now replacing a resistor with an active load is obviously not limited to a common source amplifier. Wherever you find a resistor which is giving rise to a gain, right? I mean, you are using the resistor to get a gain of GM times that resistor, which means that that resistor is can probably be replaced by an active load, right? So the obvious next step is to replace. We had this differential amplifier with a resistive load. V1, V2. This current was I0 by 2. This current was I0 by 2. And the gain was GM times RD, right? And GM times RD by 2 if you take from one side, or GM times RD if you take the difference between the both sides. So now the problems with common source amplifier and a resistor as a load, whatever it was, will still be applicable in this case, right? So which means that we can get rid of the resistor with a active load and still, by the way, I assume that you are comfortable with the idea of the problems with common source amplifier with resistive load. What is the problem? Why are we interested in replacing RD with a active load? I got jumbled up. Can you repeat?
Too much voltage drop.
Right. So you are getting too much voltage drop across RD, right? Which means that we saw that initially one of the classes that if you have common source amplifier with resistive load, you will have there is only so much of gain that you can get with a finite voltage supply, right? So if we can replace it with something with a load which is not which does not require too much of headroom to bias, right? Then we are probably doing better. We'll probably do better, and that obviously is something that we found if we use an PMOS load, right? An active load. So in this case, you can have and I can bias these voltages. Let's say V3. I can bias these two voltages and hope that this I02 currents are passing equally through both of them, and M3, if this is M3, M4, M4 are biased properly, right? If M3 and M4 are biased in saturation, then what will be the gain that I will get? assuming M3 and M4 are biased in saturation, what will be the gain that I will get between, let's say V01, V02, V01 minus V02 by Vi1 minus Vi2. What will be the gain? It will be GM times something. So what is the GM first? GM of what? You can look into your notes. GM of M1 times some resistance. What resistance? Pardon? Looking from the source side, right? So looking from the, so basically you're saying looking from here, right? Whatever is output resistance, right? Some R out. Okay, so this will be some R out. What is this R out? We'll have to figure. But it will be some GM times R out, but definitely this R out, we think it will be much more than RL for a finite RD for a finite voltage, simply because it's not, in order to bias this, you are not consuming too much of headroom, which means for a, if you had used a resistor for a finite VDD, you can only have so much value of resistance, right? You cannot really, I cannot go crazy and say I will have 1 mega ohm resistance. Moment you say I'll have 1 mega ohm resistance and you think you have 1 milliamp current flowing through a 1 mega ohm resistance, the voltage drop across it is like 1 kilo ohm, full kilovolt. So which is not sustainable, which means that for a finite voltage VDD, you can only have smaller value of resistance as a load. So we got rid of that resistance and we replaced it with an active load. And so now the question is, even before we get, I mean, this is the hope, right? This is the hope that we'll get this R out, and this R out will be much greater than RD, right? So this is we assume, this is the hope. Okay, so I mean, before we get into what will be R out and what will be RD, we need to ensure that this entire thing is biased properly. Okay, so I have just in this case connected these two, I mean, and put M3 and M4 and marked the gate to be VB3. But it's our job to figure out what VB3 is also, right? Well, you cannot leave it as is. So how do you think we can figure out what is VB3? I mean, not figure out, how do you think we can generate that magic value of VB3 for which M3, M4, M1, M2, everything is biased in saturation? Yeah, right. So I can, how do you connect, how do you ensure you already have a constant current flowing from the bottom, right? You already have I0 by 2 flowing from the bottom, which means you have a constant current source. And if you have a constant current source and you want to bias a transistor with a constant current, the simplest thing to do is diode current, right? You observe the drain voltage and take a corrective action at the gate, and that the simplest thing is, the simplest thing that we know to which does that is this. Okay, makes sense? But what is the problem with this? Or rather, do you have it will get biased. What will it get biased to? Before I go ahead too much, what will this voltage be now? What will be VB3? Quiescent VB3 will be? VDD minus VSG of M3 for a current of I0 by 2, right? Whatever that might be. So it will get biased. So, okay, fine, it is biased. Now let's assume that you have a fully differential signal, right? Let's assume that you let's assume this is Vi, this is minus Vi. Okay, or rather Vi by 2 and minus Vi by 2 if you want. Okay, so what, I mean, if I neglect GDS of M1, M2, M3, M4, what will be the voltage at Vx? Somewhere here. 0, right? It will be 0. So this will be 0. So if this is 0, what is the incremental current? Gm1 times Vi by 2. And this current is flowing into what? What load? 1 over Gm of M3, right? So this voltage will be minus Gm1 Vi by 2 by 1 over Gm3. Similarly, this voltage will be plus Gm1 times Vi by 2 by 1 over Gm3. So the gain that you are essentially getting differentially is Gm1 by Gm3, right? And that's not surprising because you are not pushing the current into high impedance, right? You are not pushing the current into a load which is of the order of R0, RDS or 1 over GDS, right? So this type of topology has a problem. That's a problem, as in you will not get, you can only get so much of gain. You cannot get too much gain. Okay, fine. So what is so now, which essentially means that we need to disconnect this diode connected stuff, right? We need to disconnect this diode connected stuff, but we need to still have negative feedback. We need to we still need some way of establishing the bias. Okay. Now note that why are we doing all these things is because we will be putting this Diffamp into some broader negative feedback loop, which is not shown here, obviously. I mean, the loop can be anything, but you can assume that there will be a negative feedback loop, and the negative feedback loop will set the output voltage. Okay. So what I'm trying to get at here is that, let's assume you have an amplifier. Let's assume you have two, I mean, in a Diffamp, you have two outputs and two inputs, right? Let's call it V01, V02. And this is Vi1, Vi2. Okay. But whatever we are interested in till now, whatever we have done till now, using negative feedback, is we're interested in only one output. Whatever systems we have designed till now has one output. Even the op-amps that you are familiar with has two inputs, one output. So let's stick to that. So let's assume that we are interested in one output, and V02, maybe that is the output. And we'll have some negative feedback here and connect it here, and that will set V02. But what is happening to V01? It is still floating, or it's not connected in negative feedback. Am I going through? So what I'm trying to get at here is that you can have one high impedance node and assume that that high impedance node will get set by negative feedback. But if you have multiple high impedance nodes, which means you will need multiple feedbacks, right, to set each of those nodes properly. Now, if we limit ourselves to the case that we are not interested in multiple high impedance nodes, we are only interested in one negative feedback line coming through, which means we need to have some feedback mechanism of setting V01. Okay, so what I'm essentially getting at here is the following. So we were comfortable with the idea that in order to get sufficient gain, you cannot have diode connection, right? So this cannot be there. But in order to set the feedback properly, we need some sort of feedback, some sort of diode connection per se. So now what we are saying is that if this is V02, this V02 will have some feedback in overall circuit, and it will probably set V02 will probably be set by overall broader negative feedback. But what is happening to V01? V01 is not in feedback. But since V0, we are not particularly interested in taking output from V01, we can still localize its voltage through negative feedback, right? So there is nothing stopping us from doing this from V01. Do you agree? Okay. So if we do this, then clearly V01 will get set to, I mean, the quiescent value of V01 will be VDD minus VSG3 of M3. And if this is, let's say, VB3, this is M1, M2, M3, M4, then we have to now figure out how do I set the value of VB3, right? Because M3 got biased, but how do I then bias M4?
Whatever voltage, gate voltage of the M3 should be done.
Yeah, so essentially, what is the role of what are we trying to achieve? If this is under, when things are biased properly, both these branches are supposed to take I0 by 2. By simply diode connecting M3, I have achieved that, because this will also be I0 by 2. And what do I need from VB3? I need the voltage of VB3 to be that magic voltage that sets the current of I0 by 2 through M4. Right? And what is that magic voltage? That I have already generated through M3 by diode connected M3. So I can simply connect it here. Right? So if I do this, then everything gets biased properly, assuming that there is an overall negative feedback that is setting output voltage of V02. Now note that at V02, if I look into V02, I don't see any diode connection anywhere. Right? So it is possible that at V02, I can still get high output impedance. I'm saying possible because we haven't derived it. Okay. Make sense? Okay, so let me redraw the circuit in a more traditional way. Now, since I only have V0, only one output, I can as well call it V0. Okay, so this current is I0 by 2. This current is also I0 by 2. Okay, so this typically, I mean, this is again a differential pair with a current mirror load, because this stuff over top is essentially mirroring the current from one half to the other. Okay. So if you have any questions till now, please shoot, because now we'll go into the analysis of this. Any questions? No?
You can tap the output voltage V0 also, just the current mirror will be.
I didn't understand.
Because here you are tapping the output as V0.
Correct.
From V0 to.
Correct.
If you want V01.
Right.
V0,
right.
so the connections will be just fixed.
Correct. Correct. So I mean, what he is saying is that, I mean, for some reason, maybe I want output from this node, right? And I don't want diode connection at that node, right? So we can follow the same argument and do this, right? So nothing is stopping you from. It's basically which arm is the mirroring arm and which arm is the mirrored arm, because the current is getting supplied from the bottom, right? We can do that. Okay, fine. So if there are no questions, let's move into the analysis. So essentially, I mean, again, it boils down to the same thing, that we want large gain, because that's what we have been doing since the beginning of the course. So if I Nortonize this circuit, that is, I want to figure out what is the short circuit current and what is the open circuit current. For short circuit current, what you do, you essentially assume that output is incrementally shorted and go ahead with it, right? So let's assume that, I mean, I'll do it in a slightly different way. I mean, I know that you are comfortable with this GM thing, but let me show you in a slightly different way. It's essentially the same thing, but hopefully it will give you a different way of thinking. So shorting the output V0 is equivalent to saying I have infinite capacitor. Right? It is incrementally shorted, as good as incrementally shorted. And let's assume that V0 is biased properly. V0 is not like close to VDD or close to ground. Okay. So if we assume that, let's now what I'll do is I'll try to see what will be the. So this is Vi by 2. This is minus Vi by 2. Okay. So what will be the, if I apply current in this way, what will be the total current through M1? Yeah, so you will have total current through M1 will be quiescent plus incremental. Incremental through M1 is GM1 times Vi by 2, right? So Vi0 by 2 plus GM1 times Vi by 2. What will be the total current through M2? It was I0 by 2. It will be minus GM1 times Vi by 2. Okay, makes sense? The M1 and M2 are same, identical.
What about Vx? Is it 0 voltage?
Okay, so yeah, good question. So what is this Vx? Is it 0? I implicitly assumed Vx to be 0. Is that right? Why or why not?
Because circuit doesn't have symmetry because this side is tied.
Okay, it's not. It doesn't have symmetry. But if I neglect GDS, then yes, right? Then it doesn't matter what is happening on top of the drain, isn't it? Because drain and source are isolated. If I neglect GDS, okay. So you can do the entire analysis without neglecting GDS also. But I mean, actually, it's a good practice. Why don't you do it with do it yourself after you go back? Do this entire analysis what I am doing by not neglecting GDS of M1 and M2. Okay. Okay. So now if you have so now if you have the total current in this stack set up like this, what will be the current through M4? So initially it was I0 by 2, but now it's a current mirror between M3 and M4, which means whatever flows through M3 has to flow through M4. So this will be plus GM1 Vi by 2. So now you have current of I0 plus GM1 by Vi by 2 flowing from the top, and current of I0 by 2 minus GM1 Vi by 2 taken out, which means there is a difference current, and the difference current is flowing into this short. How much is the difference current? GM1 Vi by 2 minus of GM1 Vi. So basically, so incrementally, even if you are taking output from one node, it is behaving like almost like you are subtracting the two nodes of where was it? Oh, I didn't draw it here. Okay. So when you had this configuration of the incremental short circuit current in each of these were what? GM1 Vi by 2, and this was flowing this side, and this was GM1 Vi by 2 flowing that side. But here the incremental short circuit current is GM1 Vi, right? It's almost like you have performed that subtraction of two node voltages through a common node, and that is happening because of this current mirror effect, right? So this part, the incremental current that is flowing in this part is independent of what is there on the load side. But you are getting an additional incremental current because you have this current mirror, and this mirroring is providing that extra current. Right? So that essentially is doubling the short circuit current. So you are still getting that extra gain, extra short circuit current gain, even though you are taking the output from only one end. That is one of the effects of adding a current mirror. Okay. So effectively, your short circuit current for this differential amplifier with current mirror load is GM of M1 times the differential voltage. What if I don't have a differential voltage? What if I have VI by 2 and plus VI by 2 both sides? What will happen? Will there be an incremental current? No, right? Constant current bias. You have both branches are trying to move current in the same directions, which means nothing. Nobody will succeed, right? So there will be no incremental quiescent current, and hence its common mode gain will be 0. Okay, but if your I0 is not ideal, you have a GDS, then you will have GDS of I0, then you will have again an incremental common mode gain, right? So those things we did with differential pair with resistive load, and all those analyses are valid in this case also. Okay, fine. So this is as far as the short circuit current gain is concerned, but we also need to find out what is the effective output impedance, right? So let's look at it. Yes. Correct. Yes. Okay, so what he's saying is that I can as well do, I can say that I can add the short, right? What is the short? I mean, the reason I added a capacitor is I wanted to show you that even without going into fully incremental model, by removing all the sources, you can still do the analysis. So if you just short it, yes, small signal analysis is still valid, but your total current equations are no longer valid, right? So what you can, if you want to still make a short, what you can do, you can say that I'll add a voltage source of value VB3. This is VB3, right? So then these two voltages remain identical. Biasing is still valid, and you are checking the current through VB3. Same thing. Okay, so now let's focus on figuring out what is the output impedance. And for this, I will do the traditional incremental analysis because it's easier to see in that picture, right? So assume that all these constant voltages are shorted, and we use all the methods that we know to find out output resistance. So first thing what we do while figuring out output resistance is incrementally short desensitize all the inputs, short open circuit all the current sources, and short circuit all the voltage sources. So this also goes to ground, and we apply a test voltage here and try to figure out what is I test. Okay. Okay, fine. So now this, I mean, obviously, if I neglect GDS of M1, M2, M3, M4 now, what will be my I test? Let's assume GDS is 0 for all transistors. What will be I test?
0.
It will be 0, right? You will get infinite output impedance also, which means, I mean, that is a bad approximation to make, right? So we'll not make that approximation. We'll assume that we need to assume that there is a GDS associated. GDS. If M1 is identical to M2, M3 is identical to M4. By the way, I didn't make it explicit, but all this assume that M3 also is identical to M4, because otherwise I0 by 2 wouldn't have flown, right? So let me call it GDS3, GDS3, GDS1, GDS1. So clearly there will be one current. I mean, the easiest of the lot is the current through GDS3. Now, what will be the current through GDS3? Incrementally, P test times GDS3, right? But we need to, but that is not the only current that is flowing on top, right? What we are interested in, what is the total current? There will be some current flowing down, there will be some current flowing up. Okay, so let's figure out what is the current flowing down first. Let me call it I1 and this is I2. So in order to figure out I1, what is the, I mean, give me some helping hand. How should I proceed? Yeah, if I know the impedance looking into drain of M2, then I can easily figure out what is I1. So if I have to figure out what is the impedance looking into the drain of M2, can I assume that the source of M2 to be shorted?
Find the 15 impedance seen by the source of input.
Yeah, but even before doing that, if somebody comes and argues that this node Vx is shorted, is that a right argument or wrong argument? Speak your mind, tell me, I mean. No, right? Why not?
High impedance, high impedance you are really that side, so it's far away from that ground.
The current source is incrementally, it's open, right? Yeah, so okay, it's not, right? So okay, as long as you're satisfied it's not, then I'm fine, I can move ahead. So then what is the what do I need to do to figure out what is the resistance looking into the drain of M2? Then what information do I need? If M2 is, if the source of M2 was shorted, if Vx was shorted, then looking in impedance would have been 1 over GDS1. Simple. So that is the reason I asked whether it's shorted. If it's not shorted, then I have to figure out what is connected, right? And what is the looking in impedance through that, right? So what I need to figure out what is, if this is not shorted, since we all agree, I need to figure out what is the impedance here. Why? Because ultimately I know how to figure out the impedance of this structure. If this is, let's say, some RL, I know what is the looking in impedance here. So I am trying to break it down into the things that I know. So which means I need to figure out what is the looking in impedance here in this direction. So is it possible for me to intuitively say what is the looking in impedance looking in the direction that I have shown here? Approximately 1 over GM. I can also say this is 1 over GM plus 1 over GDS and 1 over GM plus GDS. But I mean, if you assume GM is more than, whenever there is a comparison between GM and GDS, GM wins. And that's the thumb rule, right? So effectively, this is approximately equal to 1 over GM. Now, if this is 1 over GM, what will be the resistance looking from top? If this is, so I have 1 over GM1. 1 second. GDS1. This is shorted. Yes.
So when finding out the impedance from this side from the M1, we are neglecting that to their output. So that is because
what is neglect? We are neglecting what?
At the top drain side, there is also impedance.
Correct, right? So yeah. So his question is that, I mean, does it matter if something is connected here? If it matters, why? When does it matter? If it doesn't matter, when does it not matter? Or does it not matter anytime? Is it always 1 over GM looking from the looking through the source, independent of what is connected at the drain?
If you're already ignoring GDS1, then
Yeah, if you already ignore GDS1, it should not matter, but you have to be slightly careful. I'll give you an example. Assume that the load on top is a ideal current source load, which is an open circuit. Then what will be the looking in impedance through M1 at the source of M1? No, it will not be, right? It will be infinite. There can be no incremental current, right? Go back to the assignment, I think 1 or 2, I don't remember which one, where I had asked you to figure out the impedances of various configurations with resistances at different places. So there was one question where I asked you to plot the impedance as R0 varied from 0 to very high value, right? So there you will see that as long as this is RL is less than certain value, right? Then this impedance is fine. I mean, this you can assume it to be 1 over GM. Now, what is that value? Intuitively, you can think of it in that what is essentially happening is if you have a lot of swing at this node, right? If RL is very high, then you will have a lot of swing at that node. If you have a lot of swing at that node, then RL will take some current, but some current will also flow back through GDS, right? When we say that we are neglecting GDS with respect to GM, what we are essentially saying is that we are neglecting the effect of GDS with respect to GM. The effect of GDS is the current that the GDS is taking up. If the current that is flowing through GDS also becomes comparable to the current through the GM, then you cannot neglect anymore. So there will be a certain range of RL. There will be a certain range of RL for which you can neglect this GDS, else you will not be able to. Okay, but for most of the circuits that you will do, that you will see, you can neglect. Okay. Okay, so let's assume that you can neglect, but again, do that yourself. Let's assume you can neglect, then you end up with this configuration. And then what will be the R out? Or rather R1, let me call it, because I've been calling it I1, right? So what will be R1? Approximately? Pardon? Yeah, so GM1 times. So it's basically intrinsic gain of M2 times the load. Intrinsic gain of M2 is GM1 by GDS1. It's basically GM1 by GDS1 times 1 over GM1. But there is a catch. What is the exact expression? Can you look up and tell me? For this configuration? One over GM1 plus 1 over GDS1 plus then this extra term, right? GM1 by GDS1 times 1 over GM1. Correct? So now this is almost equal to 2 by GDS1. Right? So this is 2R0, 2RDS1 rather. So we can neglect the other terms when this multiplier term is much more, but in this case you cannot. One of the terms is exactly equal to the multiplier term. So you'll have to take both into account. So this becomes 2RDS1. So looking in impedance through I1 is 2RDS1, or in other words, the current that is flowing, the I1 is essentially V test by 2RDS1. Do you agree? Fine? Okay. So this can we or can we not? Which is greater, 1 over GM or 1 over GDS1? 1 over GDS1 is obviously much greater than 1 over GM, so we neglect it, right? So as I said, whenever there is a tussle between GM and GDS, you can assume GM to be much higher if it's transistor in saturation. Okay, so are you comfortable with this, that the current I1 will be V test by 2 RDS1? Okay, fine. So if now note that this incremental current is flowing into M2, which means it is flowing out of M2 also, right? So this will also be equal to I1. It is flowing into M1, which means also come out of M1. So this also has to be equal to I1. Or did I mess up the notations? Let me call this I2 then. Okay. So if this is so now it is flowing into M3, and M3 and M4 is a current mirror, right? Which means it has to flow through M4 also, right? So it has to flow through the GM of M4. This will also be equal to I1. So what is the total current that is flowing up then? What will be I2? I2 is the total current flowing up, right? So because of this, let me call it. We should mark it in it. So let me call it. So what is the total current flowing up? Yeah, the total current that is flowing up is I1 plus P test GDS3, right? So I2 is I1 is basically I1 plus B test GDS3, which is I1 is V test by 2 RDS1, and this is V test by RDS3. Okay. So what is that now total short circuit current? What is I test? Is basically I1 plus I2. So I test is I1 plus I2. I1 is V test by 2 RDS1, and I2 is this entire thing, which is V test times 1 by RDS1 plus 1 by RDS3. Okay. So this expression is equivalent to saying that I have two resistances RDS1 and RDS3 in parallel. Okay. So essentially our Diffamp with active mirror with current mirror load also boils down to the Norton equivalent of that is GM times VI. This is a differential, obviously, because common mode that is 0. And if you assume this to be the box where you can connect any node, any load here, this R out is equal to RDS1 parallel RDS3 or GDS1 1 over GDS1 plus GDS3. Okay, so this behaves almost as if you have this case, right? You have this behaves almost as if you have GM tank, you have VI here. This is M1, this is M3, and this is biased with some magic voltage VB3. So this here, your V0 over VI will be minus of GM1 by GDS1 plus GDS3, right? So your entire differential pair with current mirror load essentially doubles up, is basically giving you the same response as a common source amplifier with an active load. And that shouldn't surprise us anymore, because we have seen multiple times that your diff pair is essentially similar to a common source amplifier, just packaged in a different way. Okay, any questions? Note that one thing, I mean, I have neglected wherever there has been a conflict, there has been a comparison between GM and GDS. I have always neglected GDS. You can do that also, but it's a good practice to not neglect GDS and do it at least once, right? So in the exam assignments, you can neglect, but at least if you do it, you should do it once in your career, that you do the entire analysis by not neglecting GDS, and see how accurate, how close you are to the actual values. And you can also put in values. You assume GM by GDS to be more than 10, and you can plug in calculator and see how accurate you are. Right? So that will also give you some sense of satisfaction that, okay, what we had, these assumptions are not particularly bad. Okay, any questions? Okay, fine, let me stop here. Yes.
Is there any case where GDS of all transistor is comparable to GM of that other?
It depends on you. I mean, if you bias it like that, it can, right?
Okay, so in this case, we're assuming that so GM3 is much greater than GDS.
In all cases, we are assuming GM is much greater than GDS. Yes.
And impedance looking up is 1 by GM3, and that 1 by GM3 is very less than GM3.
Correct. So essentially, see, your question is it possible that GDS is comparable to GM? Yes, obviously, but easiest way to do that is have different bias current through two transistors. Let's assume the load has much more current than GM. Then the GDS of that will be much higher. Right? It's difficult to do with it. I mean, if all transistors are in saturation and you want to have GDS higher than GM, it's difficult to do it with the same amount of current. If you can change the current, bias current, then yeah, surely you can. Or you have to push one into triode. If you push in triode, then obviously GDS becomes much higher than GM. Okay. So I'll be posting the project. It will be based on Diffamp. So I'll be posting the project maybe today or maybe on Saturday. So if you have done this current mirror assignment diligently, then it should not be too much of an issue. But you will see that when you do it for the first time, right, with negative feedback, you'll see that suddenly the GDS of some transistor is much higher. Then that should trigger that maybe it's not biased properly. So if a classic case of figuring out, I mean, if you are only concentrating on the small signal parameters and you see GDS is much higher than GM, where it's not supposed to be, then probably it's in linear region. That's a safe assumption. Then you go back and check the bias points and all, right? So that is one trick that designers often use. Okay, fine. I mean, we'll discuss this again. By the way, Saturday is Thursdays, so we'll meet again. Now, all the problems of low gain common source amplifier still holds, because if your GDS is high, then you will not get enough gain, because you are anyway not getting enough gain there. So what you do, you do cascode. You can cascode here also, because ultimately, again, this is a common source amplifier similar to that. So whatever you can do in a common source amplifier, you can still do here. Okay, so we look into those things. Okay, fine.